Integral calculus is the next step in our calculus journey. So we've talked all the way through differentiation at this point, and we're on to integral calculus. And it changes its goal. The derivative, you remember, if you've paid attention along the way, is that we've always tried to find the slope of the curve. That's what derivatives do. Integral calculus is concerned with finding what's the area underneath the curve. All right. And so we could find the area underneath the curve without too much trouble if it's something like this. If it's a line and I say find the area under the curve from 0 to 2, then I set up here, it's a pretty easy process because it just forms a right angle triangle. So you just go, okay, from 0 to 2, base is 2, height's 4, because the function is y equals 2x. And you go 4 times 2 is 8, divided by 2 is 4. So we can find the area of a triangle. The issue is that there's very few shapes that we actually know the area of. We know areas of triangles, we know areas of rectangles, we know areas of circles, and trapezoids, but really there's a limited number, and they all have straight sides except for circles. But circles aren't very useful because they go all the way around. They're round all the way around, instead of curves being just round on a little bit on the top and then it being straight down from there. So what we do is we take a shape that we do know, and we're going to use rectangles. There are other methods. There's a trapezoid rule, there's Simpson's rule, there's a few other ways to do this, but we're going to talk about what if I just stuck some rectangles underneath that curve and tried to find the area. Okay, so we split the area that we want into a series of rectangles, and you can see if I scroll down a little bit that gives me an approximation of the area. The area that I actually want is this blue stuff in here, right? All of this, and then over here and up. That's all the area that I want. So what happens is when I try to find this by using two rectangles here, I've split the interval's from 0 to 1, and I've split it in half. So I've got two rectangles. And I've put the height of the rectangles around the middle of the rectangle hitting the curve. And what happens is I'm missing some area up here that I need. I have some extra stuff out here that I don't need. Missing some there, a little bit extra there, and these are pretty close to the same amount. So it gives me a general approximation of this blue area by finding the area of those two rectangles. And the rectangles are easy because they're just base times height. The base for each rectangle is 0.5. And the height of this rectangle is 4.5, let's say. Height of that rectangle is around 1.5, and we're good to go. And what we do is we try to do that using three different methods. Okay, the first method, second method, and third methods are all pretty much the same. The only difference is that one of them uses left justified rectangles, meaning if we look at that the rectangles are on the left, at the top left corner is where it hits the curve. Right justified rectangles, we'll come back in a second, are on the right. The top right corner of the rectangle hits the curve, so the height is defined by the right side of it. And then there are midpoint rectangles. In midpoint rectangles, the height is in the middle. It touches the curve in the middle. Okay, so we're just going to talk briefly about how to use each one of those. If we're using left justified rectangles, first of all, then what we do in this particular instance, we're saying that we want the height to go from 0 to 1, and I've put 4 rectangles in there. And in each case, we want the base to be the same. We want the base to be the same value. So we take the interval, which is from 0 to 1, and we divide it by the number of rectangles, and we end up with 1/4. And that is true all the time. So if we have an interval from A to B as opposed to from 0 to 1 in this specific case, then the general formula for the bases of the rectangles is B minus A, so left endpoint minus right endpoint. Sorry, the other way around, right endpoint minus left endpoint. Left and right, I'm okay. Divided by the number of rectangles. And then what we do is we say, okay, now what's the height of the rectangles? And because they're left justified, we're going to start with the left corner of the first one at 0, and we're going to go up to the function. And we call that right there f of 0. That's the height at 0. In this case, it's 6, right? Whoa. F of 0. There we go. Then this guy is f of 0.25. This guy is f of 0.5. And this guy is f of 0.75. The heights are the function defined at that point. And so f of 0.25, we don't know what this function is, but we can read it off the graph that it's 4. This is about 2.5. And this is about 1 and a bit. So I'm going to say 1.3. Okay? And we take those heights and we multiply them by the base. And when we do that, we get our area. So in general then, we start at the left endpoint and we just add the base until we get to the right endpoint minus 1 base. So in other words, we go, if you look up here, we went, the first point was 0, right? Then we went to 0.25, that's 0 plus the base, because the base is 0.25. And then we kept going until we got to 1 minus 0.25, 0.75. So the area for a left justified rectangles looks like this. All right, that's the sort of general formula for it. If we do right justified rectangles, all that changes, the base stays the same, but all that changes is instead of starting at the left endpoint, we start 1 base from the left endpoint. So we actually start here, and we go all the way to the right endpoint.